Hi everyone, I'm Ari, and I'm going to be covering problem 2 of the Dynamics homework. I picked problem 2 because it's probably, I thought it was the hardest problem of the whole homework, and there was a few specific things that I couldn't really find clear answers for online, so I'm hoping that maybe someone will see it and say, oh, that's wrong, or maybe they'll be like, oh, that's how I did it. So we're starting with an RRRP robot. We're given this image kind of showing us that all of the angles are about the same axis, and we have a linear actuator over here, and we're asked to evaluate it at the angles 0, pi over 2, negative pi over 2, 1 for all four of our joints. So first of all, we are told to use the product of exponentials, which I like less than the other method, even though the other method's worse. But that's just a personal preference. So first of all, we need to define our M matrix, which is going to be our zero configuration. Looking at our zero frame and our body frame, we can see that it is not rotated, so that's just going to be the straight identity matrix. We can also see going from one frame to another that we have this L1 plus L2 in the y naught direction. And then the thing I was, iffy about, I think I looked at another person's homework and they had put a negative L naught here. Now, I'm not entirely sure for the zero position matrix if we're defining it from our zero frame up to our body frame, or yeah, space to body frame, or the other way, because the way I thought of it was we're at zero frame, we're going up a distance of L naught, now we're at our body frame, therefore it should be positive, but it might be negative, and when I looked around online, I saw some sources that said one thing and some sources that said another, so I wasn't really sure. So ultimately, this is what I ended up using, but that might be wrong. So then we have our M matrix. Then we need to find all of our screw axes, our twist essentially. So the way we do that is, first of all, the angular component's pretty easy for all of these. They're all about the same z-axis, so they're all just going to look like 0, 0, 1, 0, 0, 1, except for our linear actuator, our prismatic joint. That actually has no angular acceleration for some reason. It's almost like it's not spinning. Then, for this first joint, you pick a point, you cross it, you make it negative. Uh, right here, it's the distance is gonna be 0, so it's just gonna end up with the 0 vector in the tangential velocity. But then we get to our second joint, we pick a point, distance L2 in the y naught direction, we cross that with our omega, and then we put in a negative sign out front. You have a z cross y, that's going to give you an x. I think that gives you a negative x, and then the negative out front cancels it. Same thing happens here, it's just L1 plus L2, that y vector that's bigger. And then for S4 it doesn't matter because we just have that tangential, we just have that linear actuator. I also wrote them in a matrix form where like the top right component is the skew matrix of the angular velocity, and then here's just our tangential velocity, and then just a bunch of zeros to fill out the matrix. So then we have the big ugly formula for the product of exponentials, which is just going to be e to the skew matrix times our joint. Do that for all of the joints. So we're going from here to there. There's 4 joints. We have 4 of these terms, and then multiply it by our zero position matrix. So I did have to look look really hard online to figure out how you take the exponential of a matrix. Ultimately, what I got from like the what's it called, the textbook and stuff, was this formula where you have this top term is just e to the skew matrix, but now of the angular velocity theta, and then this equation, I believe we derived this in a video. I cannot remember the name though. And then 0, 1, which is kind of the pattern with all of our homogeneous transforms. And then EW theta is given by this equation that we were also given the name of Rodriguez, maybe? I don't know. I can't remember. So I started by simplifying it by plugging in our actual thetas. I thought about trying to solve it symbolically, but it's very ugly. So immediately for theta 1, that's 0, so we know that that's just going to be the identity matrix because e to the 0 is 1, and the matrix equivalent of that is the identity matrix. Then for pi over 2, I went through the slow process of plugging stuff in. There was luckily a lot of zeros that cancel out, and we end up with this 0, negative 1, 0, 1, 1, 0, 0, 0, 0, 1 matrix for pi over 2. Then we get this for, what's it called, for the negative scenario. And when we get to our fourth joint, that because this is a prismatic joint, I think this entire term simplifies to v theta, I think. V theta. Yeah, so it ends up basically the identity matrix with its tangential velocity just tossed in there. Then I went ahead and multiplied them all by hand, which was probably a mistake. I probably should use the calculator, but I did the whole thing. Ended up with this as my final matrix. Uh, it was interesting because I felt like I could look at this matrix, I could look at the problem, and I could have gotten there kind of on my own without the whole process. Uh, like, there's no rotation being applied, and then we're going up some L naught, we're going up 2 in the Y. Uh, I don't know. Anyways, uh, then we needed to find the inverses for the body form, which I kind of did as like a double check to make sure my matrix was right. I started by inverting the what's it called? The what was it called? The zero position end effector matrix. I don't think that's the actual name. I don't remember the name of that matrix. Uh, but I started off by inverting it. Then I did the 80 of the matrix, which luckily is defined for us kind of just as the rotation matrix 0, then the skew of the position vector times the rotation matrix, and then the rotation matrix again. Luckily, in this scenario, the rotation matrix was just the identity matrix. So you can see two identity matrices, and then this is just the skew matrix of the position vector. Uh, then we end up just multiplying that by our SI matrices from earlier. Actually, no, it was by our SI vectors because this is a sits by sits, and then these were the vectors are sits by 1. Yes. So then you end up multiplying them, you get these vectors, and then you can go ahead and work it out that if you have M on the left-hand side now, and you do E to all of these vector skew matrices, which would just be repeating the same process I did earlier, but you can work out that you get the exact same homogeneous transformation matrix. So anyways, that was my work for problem 2. Like I said, not entirely sure about this negative sign. I could be just maybe misunderstanding we're like looking what this matrix is built in reference to. I'm not even entirely sure what it's called, as you could tell by the fact that I kept forgetting. Uh, but yeah, so that was my work. Please let me know if you spotted any mistakes or anything. Thank you so much.